consultant with ESIG. I want to welcome you to our monthly webinar series and give you a little bit of background on ESIG. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of renewable energy and energy systems integration decisions. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials. We also serve in a leadership role with the Global Power System Transformation Consortium, the GPST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of the 5 pillars, which deals with the research agenda for the system operators. More information on the GPST can be found at globalpst.org. We just completed the planning and posted the agenda for our ESIG Fall Technical Workshop, which will be held in Providence, Rhode Island, during the week of October 21. We have a great lineup of current topics and speakers, including a field trip to see the Block Island offshore wind plant, the first one in the U.S. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the ESIG website. If you're new to ESIG, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces. You can find us on the web at esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Okay, just a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we use the Slido platform, so please ask your questions through Slido. Go to slido.com and enter ESIG20 as the event code. The instructions are also at the bottom of this screen. You'll see a thumbs up button next to the questions to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 minutes or so for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today's topic will be on EPRI's Low Carbon Resources Initiative. EPRI and GTI Energy are together addressing the need to accelerate development and demonstration of low and zero carbon energy technologies. The Low Carbon Resources Initiative will focus on large-scale deployments to 2030 and beyond. Fundamental advances in a variety of low-carbon electric generation technologies and low-carbon chemical energy carriers, such as clean hydrogen, bioenergy, and renewable natural gas, are needed to enable affordable pathways to economy-wide decarbonization. This is a topic that is also central to ESIG's mission to help identify pathways to 100% clean energy. And it will be presented by Jeffery Preece, a Director of Research and Development at the Electric Power Research Institute. Jeffery, in his role at EPRI, is focused on developing cutting-edge research portfolios to support the energy transition to a net zero emissions future. Jeffery leads EPRI's research teams focused on long-duration bulk energy storage, advanced power generation cycles, CO2 capture and storage, net zero industrial clusters, and hydrogen and low-carbon fuels. Jeffery serves as EPRI's lead on the joint EPRI-GTI Energy Low Carbon Resources Initiative, and also worked in engineering and operations at U.S. electric utilities. EPRI is a regular participant at ESIG, and I feel very fortunate to have Jeffery here with us today. Today's webinar will explore a number of different questions relevant to the future of integrated energy systems. How might low-carbon fuels support goals to achieve net zero emissions while maintaining affordability and reliability? What is needed to increase deployment of new low-carbon technologies? How might the anticipated increase in electricity demand in AI, data centers, and manufacturing affect net zero targets? This presentation will highlight EPRI's approach to understanding net zero energy systems, supporting accelerated deployment of advanced technologies to make, move, and use low-carbon fuels, and demonstrating how the electric system will be an integral part of the future net zero economy. I greatly value the contributions of EPRI to the industry, and I look forward to what Jeffrey has to say. Just a short reminder once again to use Slido at slido.com with the event code of ESIG20 to ask your questions. Okay, without any further ado, let's go ahead and get started. Jeffrey, I'll now turn it over to you.
Thank you, Charlie. It's a pleasure to be here, and we appreciate the invitation to speak to the ESIG group, and look forward to engaging with you participants through the Q&A. So please pass those along. If Charlie said we can't get to them, we'll be happy to follow up. Brief intro about EPRI. We're also a nonprofit organization, 501c3. We've been around for more than 50 years, working to collaborate across industry and other stakeholders in support of objective and independent science-based research that helps society advance a safe, affordable, and environmentally responsible clean energy transition. We have a global footprint working with organizations from around the world on advancing these technologies and insights. And the one word to describe EPRI is collaboration. We believe very strongly in putting the best minds from around the world on the hardest challenges, whether they be within our organization or with others. And we're always happy to talk to folks about how we can together shape the future of this energy transition. Our view of the future of energy revolves around this unprecedented amount of change which is before us. A couple of years ago, when we first started the initiative, which I will talk about, we were just at the beginning of establishing net zero targets as a society. Countries, companies, regions looking at decarbonization in response to largely Paris Climate Agreement and maintaining 1.5 and less than 2 degrees Celsius for climate change impacts. And that decarbonization journey has certainly been one that the industry on the electricity side has been on for a number of years, transitioning from coal to gas. But now we're looking at this more broadly and, more importantly, as an integrated solution set to energy. And so decarbonization has been taking place through electrification that will continue on the gas side, mitigating methane emissions. But then as we look to the future, this transition is quickly becoming a transformation, a fundamental change in the way we make, move, use, and rely on different energy resources. And on top of that, there's an added factor of resiliency, that as climate and weather start to impact our day-to-day lives and the energy systems we rely on today, as we anticipate more of those changes coming in the future, as we anticipate the integration of and the needs around cybersecurity, artificial intelligence, machine learning, there's a lot that still has to be done to integrate the data, the systems, and the analysis. But the bottom line for the future of energy is it has to be clean, it has to be affordable, and it has to be reliable. And those will be common themes throughout the presentation today. When we approach the pathways towards a decarbonized future, we love to talk about new technologies and the excitement and the potential that they bring. But we're really building on and need to continue to invest in some of the technologies and approaches we already have at our availability. Energy efficiency needs to be at the forefront of all we do. Not using that electron, not using that molecule is the best way to reduce our carbon footprint and provide meaningful progress towards decarbonization. We have to continue working towards an efficient deployment of clean electricity and the electrification of industries where that makes sense, and really focus on the hard parts of our economy where low carbon fuels, carbon management through capture and storage play a role in getting us to that final decarbonized future. And of course, it doesn't stop once we get to a 2050, 2060, whatever the goal might be for the country, the region, or the company, 2030 in some cases. It's a continuation beyond. It's one mile marker that we're working towards. But that energy system that's being developed has to maintain that affordability and reliability well past the decades of achieving those targets. As I mentioned, we started this initiative with our partners GTI Energy back in the 2020 timeframe. And at the time, only about 10% of the global greenhouse gas emissions were covered in various national targets. And what that means, some of them law, policy, some pledged, some proposed. Fast forward to this summer, June of this year, almost 90% of the greenhouse gas emissions are now covered. And you can see kind of the breakdown of how they're solidified based on these national targets. So in just 4 short years, we've seen a tremendous amount of attention being paid to setting these targets, and then now, of course, figuring out how are we going to get there. EPRI's approach, this is an older report. It goes back to the foundation of this initiative, looking at economy-wide emissions. This is only for the US. Certainly, it could be representative of many other countries around the world. But the US story kind of paints a picture to compare to. And that is, there's a strong role of electrification. 20, 30 years ago or so, electricity was 2% of our energy source. Today, it's about 20%. In the future, 2050, if not a little bit before, could be as much as 50% of energy that we all use as energy consumers from electricity. And when we look at the role that the electric sector plays, it has a strong ability to get the entire energy economy closer to that net zero role, but we can't get there through electrification. And so that's where low carbon fuels, carbon management, and other technologies and approaches come into play. And that is really the focus of this initiative that we've launched a couple of years ago. And what's been really interesting, this is a somewhat anecdotal approach to what's happened in the conversations around net zero. First, it becomes defining what is net zero. What is zero? Are we going for 100% renewables? Are we going for zero carbon? Is it renewables plus nuclear? Is it any technology as long as anything that's any carbon put in the air is mitigated through any other means? There's a number of questions and approaches. And we're seeing less and less of that question, but it's still very relevant as folks, organizations, countries decide on where to align on net zero. And then the conversation will shift into, well, what is the status of some of these technologies? How are we mitigating CO2 from point source emissions or pulling it out of the air? Where does hydrogen, ammonia, or e-fuels come into play? Where are they now? What does it take to get them to be deployed? We have existing assets. We're building a lot of new assets with the same technologies, gas turbines, engines, boilers across industries, not only just power. Can those assets that we're using use low carbon fuels if we have them in the future, or can they be retrofitted? And how do we prove that? And then it comes to, well, how much is this going to cost? And how are we going to get these fuels? And how can we know that they're going to come into our facility reliably and affordably? And what's the infrastructure that's required? And then are we the only ones asking this question? Are there others around us geographically where maybe we have shared resources because it took 100 years to get fossil fuels to where they are in terms of their availability with infrastructure and delivery and storage? And we're talking about changing parts of our energy system in about 30 years. So if we partner together, are there opportunities? And then the conversation usually goes a bit bigger globally. Who else is doing this? Who is well positioned with energy resources, with a supply chain, with surplus of renewables that could turn these excess electrons into low-cost molecules, or sitting on top of CO2 storage sites for low-cost management? And then now I think we're finding ourselves as a society thinking more about, well, what's reasonable in terms of the timeframes and the cost to deploying technologies at scale. And with all of these questions, how are we going to resolve this future, and what is it going to take? And that essentially is the LCRI in a nutshell. All those pieces. We are touching every part of that, of those questions, every aspect of the technology, the deployment, and working with stakeholders to understand how to accelerate in a very narrow time frame this transition in order, again, to maintain through the transition and at the outcome an affordable and reliable energy system. So our view is that sometime in the 2030s, we would need to see the deployment of low carbon fuels, energy carriers, which means they have to have a value chain established across the different end users. And all of that means very different things based on your geography, your region, and your capabilities. But to us, 2030 is a big decade for the role of low carbon fuels. And our focus within the initiative is understanding the landscape of the technologies in this decade, conducting evaluations at the pilot and the demonstration scale in order to get these technologies, get these approaches, get the knowledge, the learning, the environmental, the workforce, the safety ready for that larger scale deployment and integration in the following decade in 2030s. Because it's going to take at least 2 decades to get these technologies up to commercial scale to make an impact on mid-century net zero. At the same time, our energy system is integrating and has the potential to integrate more and more. So here's what it looks like today, very simplistically. Primary energy sources on the left, moving, storing, getting those energy sources on the right. The energy system we're looking at in the future looks more complex because we're talking about electrons making molecules, molecules serving electrons, carbon management from different sources to different sinks, energy systems with biofuels that can go and serve gaseous or liquid molecules and end users, retrofitting existing infrastructure for new fuels and molecules, or building new infrastructure where that's not sufficient, and then creating synthetics where maybe you can drop in those fuels with the infrastructure if infrastructure becomes the bottleneck. But then, of course, energy and economics and first principles become the challenge. So we use kind of this perspective as we think about where and how these molecules and energy carriers play a role. But of course, everything is changing quite rapidly. And thinking about this as a systems level also requires critical thinking and rethinking as new information comes to light. One of the first major outcomes of the initiative that I'll point you to is our US economy-wide net zero scenario analysis. There's a link here. It's publicly available. If you haven't seen it, I encourage you to check it out and give us feedback on it. As I'll say at the end, we're updating this analysis, which was done in 2022. So be on the lookout for that. There's a ton of material in that analysis, but one of the main takeaways is depending on where the energy transition goes in terms of technology, cost, availability, and performance, in terms of the cost of fuels like natural gas and petroleum products, in terms of availability to have certain technologies in the mix. So in one case, in the limited options, you'll see here, we've restricted CO2 storage. So can't put CO2 underground for whatever reason across the entire country. It also restricts the use of biofuels. And so across the different scenarios, all options where everything is there, higher fuel costs, largely around natural gas, limited options, no CO2 storage, no biofuels as a predominant source, different technologies would need to deploy at different times. And this is an economy-wide, across the country look. Every region will have its own unique perspectives. But the important part is there is no one size fits all. And so how can we talk about an energy transition? How can we plan an integrated system where we already know our electric grids don't integrate across the US? They don't integrate in every country around the world, some more than others. But now we're also talking about a global ecosystem where we're dealing with commodities that are traded like gas, and methanol, and ammonia, serving other purposes in the energy space that they don't. And how does anybody or any country try to plan that out and move forward with the net zero strategy? Another example from this analysis, which speaks to that hard to decarbonize part, and largely becomes a somewhat difficult conversation to have, is the role of gas and gaseous fuels in our system and our economy today. So on the left side, you see what that all options case means for buildings in the US, and I'm only showing the eastern part of the US or so. And you can see that to decarbonize buildings, to get them to net zero, you see a lot of orange. That's natural gas. That means that there are offsets of carbon coming from somewhere else in the energy economy, largely from biofuels with CCS creating negative emissions. So in the MISO East area, in the Mid-Atlantic, areas where you have in the Ohio Valley, where you have colder winters, still need that backup fuel of gas to get through the colder months. You have heavy industry relying on high temperature. That all options case allows CO2 to be managed in a way that offsets those CO2 emissions from those areas in the buildings. And that comes up to a marginal cost across the whole energy economy, not just buildings, the whole energy economy, $165 per ton of CO2. And then you can see as we go through more stringent cases, the one on the right being the most, where again, no CO2 storage, limited amount of biofuels, electrification goes up incredibly compared to the all options case, but we still rely on molecules to support the energy demand in the buildings. And so that comes at a price, of course, order of magnitude higher, $1,200 a ton for CO2. Now, these are not meant to predict the future. These models are wrong. They're filled with a lot of assumptions. They're not going to say what it is in the next 5, 10, 15, let alone 30 years. But they give us good insights into understanding the intricacies and the balance of our energy system in a way that really hasn't been studied in full degree and still needs a lot of work. And we're happy to be collaborating with ESIG and others on these very same questions. So that's the 2050. But then, we start this initiative in 2022. And of course, now we're living in a very different world. So net zero was the big focus. Now let me kind of go through some intermission, if you will, about what's happening in today's environment and how that's changing. And we say we're reaching this inflection point where that transition we used to say in the 2020s is now becoming a transformation because of three main factors. We're seeing an unprecedented amount of demand increase on the electric sector. We're seeing the supply of electricity and energy changing rapidly. And we're seeing the impacts of weather today, where maybe we didn't see them for decades or anticipate them for decades to come. So, of course, a lot of buzz and a lot of interest in artificial intelligence and data center growth. You start data centers and digitalization's been around. First wave, social media, cat videos, Facebook, liking posts, Instagram, all that's happening. Second wave, everything is moving to the cloud. A lot of our infrastructure, resources, backup storage, management of systems going to the cloud. And now we're entering this third wave of artificial intelligence and, growth projections 2 to 15+%. It's anybody's guess at this point. But what we think about in terms of artificial intelligence, retinal scans in airports to identify passengers, screening for boarding passes, based on cloud software and AI, that's one thing. But also there is a race to essentially create the human brain. And that requires a lot of processing power as well. So when we say artificial intelligence, we have data centers and low growth, but there's also a very strong underlying current of energy security, replicating the human brain, taking the capacity of human thought forward through machines. And that requires and would require a whole lot of energy. The second area on supply. We're obviously seeing a lot of growth in renewables. We're seeing a steady growth in gas. We're seeing a lot of that gas being offsetting retirement in coal. But as I mentioned, the regional aspect of this is very important. So here's a snapshot, June 18th of this year, from MISO, SPP, CAISO, ISO Northeast, and ERCOT. And no surprise, everybody's different. Everybody has a different resource mix. Everybody has a different generation profile. Maybe there's some commonalities in terms of capacity across different lines. Certainly there's trading going on across many of these parts. But how can we talk about an energy system when the electric grid, the supply, is already diverse, already changing, and will continue to change quite rapidly over the next few years? And we somewhat anticipate that as we see this change happening, more renewables, less coal, maybe steady output of nuclear, potentially some bump ups if advanced reactors come online in the next couple decades. But one of the important parts that we're seeing is we have events occurring within this energy transformation already happening to the grid. So 3 examples on the right. The data on the left shows you one in April, shoulder month, we call it on the electricity side. So spring day, relatively mild temperatures, a lot of generation assets take an outage, they're offline doing their repairs, and there's planned to be a lot of capacity there to support the load based on that time of year. But what happened here in Alberta is they ended up having a load shedding event, 250 megawatts to stabilize the grid. One of their gas units tripped, went offline. And as you can see, the wind capacity wasn't there, operating at 6% of its nameplate. And so as this energy transformation takes place on the electric sector, uh, the the shoulder months typically hadn't been affected by this energy transition because we're pretty good. Grid operators, planners, system designers, generation companies, they're good at looking at the future and understanding weather patterns and loads. Uh, but with this transition comes new and unexpected conditions, and unfortunately, the weather doesn't always cooperate when it comes to renewables output. And so again, that reliability piece becomes really critical to this transition. And the last thing that's happening right now is the immediate impacts of weather and climate. And what the projections show is that sometime between today and the next few decades, we could, based on where warming goes out to 2030 and beyond, see a significant increase, factors ranging from 2 to 9 times the impact of the weather and these events. So storms happening in the same area more frequently, costing more money to recover every time they do occur. Wildfire risk increasing and becoming more prevalent. And when renewables and the transmission systems are designed and built in those corridors where wildfires are a predominant risk, obviously reliability and resiliency become a factor. And so taken together, there's a lot of things already happening to our energy system in our transition, let alone this target to get to a net zero future. And we at EPRI and many others have largely maintained this perspective that technology and solution optionality is the way to get to an affordable and reliable net zero future. And that optionality is not just within the type of generation sources we have, where our energy comes from. It's also in how we manage and design our grids, how we expand and use technology like grid enhancing technologies and resources, advanced demand response, energy efficiency, customer interactions, markets, regulatory policy. All of these options need to be on the table. And they have to be part of this ecosystem that goes into designing and supporting this energy transformation. The initiative subject to this talk, though, is really focused on the technical pieces, but really want to highlight where we go with technology deployment has a role in a broader and bigger ecosystem. So we've got net zero targets. We have unprecedented low growth happening in the electric sector. We have a rapidly changing resource supply on the electricity side. We have our energy system being impacted by weather and climate effects, and that expected to continue. We have less than 30 years to get to a mid-century net zero target. And the other challenge is it takes time to develop these technologies. The good thing is the energy system has been very successful taking technologies from concept to full commercialization. And as I mentioned in the beginning, and Charlie did in his intro, our position within this initiative is to figure out how we can accelerate certain parts of technology and the integration to really try and shorten these timeframes, because the timeframe we have set for ourselves is already shortened by the standards we can measure from the past few decades. The other challenge with this, but really it's an opportunity, is that while decarbonization options vary by industry, there's a lot of common themes that if we integrate and have a holistic vision and look at this at a systems level, talk to stakeholders to educate and understand the roles of these technologies, no industry has to do this alone. And certainly there's certain parts like energy efficiency and electrification and demand response around our energy, not just electricity, that are going to help along the way. But the challenge of getting to net zero, of deploying these technologies rapidly, needs to be one that isn't done in silos with every industry going on their own. And so being very clear about what makes sense and maybe doesn't make sense from industries is one of the first steps that can be taken. You've probably seen a lot of news around hype cycles and the booms and busts of hydrogen as one of these low carbon fuels, and that's going to happen. We don't think that that's an issue. We see technologies and approaches come and go, but as long as society and the industries are learning from those cycles, we tend and we have a history to show that there will be progress in these technologies and their deployments. The key is, and the hard part is, of course, maintaining this transformation with that reliability and affordability in mind. So, what does it mean to be integrated? Again, I mentioned integrated. I showed you the slide deck, but it's not just integrating the technologies. That's one part. It's not just integrating the infrastructure. That's another critical role. Doesn't get a lot of talking points and coverage, in my opinion. We need more talk on infrastructure. There's a lot of talk on energy security. That's certainly increasing, especially in the race to AI. But there's a lot of potential in the economics and the job space, in the coordinated policies when we think about low carbon fuels and CO2 management. And these topics on the right are really the values that come out of this integrated approach if we can stack them and design for them going forward. So, of course, we're trying to maximize emissions reductions, but which industries, which sectors have to take that on first? Well, the economists will argue that there's an economic pathway if you study these systems, an industry, steel mill next to semiconductor manufacturing with power plants and residential and commercial uses. You can design an economic transition for that cluster of organizations, companies, individual consumers, and maximize the emissions reductions according to an economic route of decarbonization. In doing that, it can help you manage the risks, align against flexibility and policies and environmental, and get that sustainability. But that in and of itself is a challenge, and coupling sectors is not a new phenomenon. We see that worldwide, as regions have developed industrial clusters and hubs, if you will. But how and where that's done becomes a critical portion of this energy transition. And just making sure people are aware and they're talking about it in this way is really important. Okay, so more about LCRI. We're really focused on taking these concepts and getting them to deploy. That is our number one target. And we've set out to create a global collaboration. We have more than 60 organizations participating from around the world, focused on applied technical research and knowledge sharing, leading towards demonstrations and providing resources and tools that can be used going forward. So we started in 2020. We built the foundation. What are low carbon fuels? What are energy carriers? What are net zero targets? What does it look like for a country like the US to make this transition, the all options, the limited options? What technologies have gaps, and where can our initiative between the efforts of EPRI and GTI Energy and our members help accelerate this transition? So now we're at a cross point with this initiative where we've done a lot of work already. Encourage you to go to our website, find information. There's a lot of publicly available resources there, and really trying to work towards getting technologies in the field, and not just one-off technology, showing how they integrate. All of this is about integration with the electric side, with the gas side, electrons, molecules. It all has to come together. And so a couple of examples of what that looks like. Hydrogen gets a lot of talk. It's been around, it's had hype cycles. Really, we have to figure out, where does hydrogen make sense? It's going to make sense only in certain regions and certain applications. And how do you get the regional engagement to understand its value, understand its gaps in a productive way? And then what are the technologies that need to be advanced in order to move forward? And because this is a presentation with ESIG, Want to share with you one of the learnings that we've pulled looking at integrated resource plans on the electric side related to hydrogen and modeling. And you can see 4 buckets where most of the IRPs filed don't mention hydrogen yet. These are IRPs, so they're looking out in a relatively short time frame. But we're seeing more and more starting to have awareness, some incorporating modeling, and very few actually making assumptions in there. And why is that? Well, obviously it's complicated. An IRP on the electric side doesn't always address the fuels component of hydrogen on a market dynamic. But we've developed resources to help organizations understand and plan for and educate their stakeholders on what this could look like. So a couple of resources here. These are all publicly available. Please check them out. Give us feedback. The first one, we look at hydrogen with renewables. We have a techno-economic calculator that allows you to generate a levelized cost of hydrogen based on our own independent evaluations of cost for different technologies, and gives you a range of capital, operating, and sizing that you can use to then go put into a system planning model. We've also conducted a number of analysis at the systems level, and then specifically in this example, shown what some of the impacts of the Inflation Reduction Act and the 45V production tax credits might have on the cost of electricity, that levelized cost. And then as you can see on the bottom, what a operational facility relying on, in this case, we assumed all 3 pillars, so additionality, temporal matching, and regionality were assumed, what that looks like and what those costs might be. So getting resources into the hands of stakeholders, again, that knowledge capture, that understanding of technologies, what it's going to take to deploy these technologies moving forward is very critical. And then we look at maybe some other areas that aren't as obvious on the surface, but looking specifically at what Inflation Reduction Act and the bipartisan infrastructure law are having on this, again, transition. And this is a great example of the integration of not only the gas network, but CO2 management, ethanol production, hydrogen, methane, all the work. So here, this is a very high level feasibility study where we looked at all of the ethanol, CO2 from ethanol production and how much it would cost to, based on different scenarios, make methane from CO2 and hydrogen and use the existing natural gas infrastructure to supply what we call e-methane or a net zero methane to exports, in this case, looking at Japan. And so you can see the impact of the tax credits, very significant, getting down to roughly $20 a million BTU. Japan typically imports at around $12 to $15 per million BTU. So, not too far off, very early stage feasibility study, a lot more can be done. The impacts of CapEx, of OpEx, of transitioning, synthesizing methane from CO2 and hydrogen still in development at small scale. But nonetheless, again, you're starting to see some pictures of how integrated electrons, molecules, CO2 management, bioresources could come together. Another example, equally important to the integration, are the people. And under this initiative, we have the ability to lead the U.S. Department of Energy's only hydrogen workforce development program. And we're more than happy to extend this to others. So if you have a workforce need or a workforce opportunity with universities, let us know. There's also a lot of really great resources at your disposal through this effort, looking at how hydrogen could help transform the energy economy, but also some of the fundamentals around safety, environmental aspects, hydrogen use cases. And so we appreciate the funding support and the partnership with the U.S. Department of Energy on this endeavor and many others as well. Okay, and then the other thing I mentioned was demonstration. So far, the initiative, what I presented, understanding what net zero is, building those resources, the capabilities of low carbon fuels like hydrogen, carbon management, biofuels. But really, we're working towards getting things in the field, testing them out in an integrated way. So a couple of examples to build off of. The first one here, we're working with NREL and the National Renewable Energy Lab outside of Denver to operate a just over 1 megawatt electrolyzer system, and working with them to develop system characteristics of what it looks like to match renewable energy electrons, solar, wind primarily, with hydrogen production, and how to integrate at a site level with those operations, and what that will do to not only the electrolyzer operation but to the grid, because perhaps there's some ancillary services or grid response mechanisms, uh, and integrating at a very large scale is something that hasn't been done in many places in the world. In the middle, though, I mentioned infrastructure. One of the ones we're participating in is another Department of Energy effort called HyBlend, that's looked at how to use the US's existing natural gas infrastructure to deploy hydrogen. And this is a big challenge because the US natural gas infrastructure could be relatively new in some parts of the country, relatively old in other parts, and not a lot of good characterization has really happened at large scale, despite being able to transmit and distribute and store natural gas across the entire country. So a lot of great work going in with the partners at the national labs and other stakeholders to understand the benefits, the costs, the risks, and evaluating that infrastructure. And then, of course, hydrogen has always had this, and low carbon fuels to a broader extent, this chicken and egg dilemma. You have end users who say, okay, I recognize I need to decarbonize, I need a new low carbon energy solution, but I'm not willing to pay more than whatever amount, either what I pay today, maybe a little bit more, maybe less. And then you have the producers and the integrators who are saying, well, in order to get you that price, I need economies of scale. And so this balance of where are the end users, where are the producers is always a challenge. You see efforts like hydrogen hubs, which I'll talk a little bit, come out that try to break that cycle. You see 45V and tax credits, 45Q on the CO2 side, trying to break that cycle. And then you see demand support coming out of DOE and Office of Clean Energy demonstrations for hydrogen as well, $1 billion being used to help buy down the cost for end users. But really what we hear when we talk to end users is it tested? Is it true? What is it really going to take? What does it look like when it's operating? And how do I know? How do I choose? I have all these options, these technologies. So our in-use portfolio is really focused on educating, getting data objectively, independently, and studying this again, not only at a technology level, but at an integration level. So I'm going to give you some examples, sticking with the power generation, but we do a lot in industry, mobility, and other parts, but just highlight some power generation. So for natural gas, there's a few options that are being considered in this journey to net zero. You can retrofit and be able to use a new fuel or a new energy source. You can repower your existing asset, or you could come in completely new asset. And within those options, you have more options in terms of, do you do a drop-in fuel like a biofuel? Do you start blending low carbon fuels, hydrogen percentages, ammonia perhaps? Then do you go to point source capture? So you put carbon capture on the emission side of that power generation asset. And then in terms of the most complex, switching completely to 100% low carbon fuel. And of course, that's not the only factor that goes into this, because with natural gas, the full life cycle has to be considered. Some parts of the world don't have a reliable supply of natural gas. Some countries heavily importing, some states not accessing new infrastructure for natural gas supply, already limited, public perception, costs, et cetera. There's a lot that goes into this, so it's not very simple. But when we look at this, we're trying to understand where and how, again, time frame, net zero 2050, that's a target, but the transition is also important to this. So what doesn't get a lot of attention right now more broadly in this space are the opportunities with low carbon fuels, renewable fuels, biofuels. There's a lot of characteristics that go into this. I'm being a little bit vague on purpose. But within this portfolio, we're helping to evaluate the supply chains, again, the logistics, the infrastructure. Some of these are meant to be drop-in, but they haven't been proven to be dropped in. So we anticipate that when you combust a biofuel that has a similar properties, similar carbon, hydrogen links in the chain as a fuel, that it's going to give you the same performance on the back end. And then, of course, that life cycle, it's going to match up in a way that meets the net zero targets. And then how do you use that fuel long term? And then, these fuel sources are different. And with that difference comes opportunities to engage the community, opportunities to improve local air quality, in addition to greenhouse gas emissions reductions. And we're seeing a lot more interest and investment on the community side to understand the impacts, especially with existing assets. Because if you can keep a power plant where it is in a county, in a city, town, and transition the fuel to be low carbon, that brings benefits to that community, in addition to the environmental side. So we have a number of resources. Again, I'm putting these out there so that you'll check them out, give us feedback on it. We have a database that maps the potential sources of renewable fuels in the US, that Renewable Fuels Atlas. And then we have a fact sheet out there that goes through the different types of fuels that are part of this transition. And in addition to the work that we're doing, evaluating the role that these fuels play or could play. The other area that gets a lot of interest so far in terms of power generation is the use of hydrogen. So here you can see where we've supported 4 demonstrations of hydrogen blending in natural gas power generation, 3 gas turbines, 1 reciprocating engine. The percent volume is the amount of hydrogen that went into natural gas. Important though, none of these tests ran more than about 8 hours. So short duration, very high volume of hydrogen, but short duration. None of these started up or shut down on hydrogen. None of these technologies or these equipment represent the full suite of equipment that's already out there operating today. So this is a good first step. And of course, there's a lot of questions around, well, is this viable? You're talking about making electricity, making hydrogen, and turning back to electricity. That sounds like there's a lot of energy loss, and there is. This isn't something that happens consistently, electron to electron. It's a long-term energy storage play, and maybe specifically if you're sitting on top of a large salt cavern to store that fuel and have excess renewables nearby. But nonetheless, it's too early to tell in some cases. And again, technology optionality is critical. And so here you can find a report that looks at how ready are some of these gas turbines. How ready are they to be ready, we like to say, for low carbon fuels. And unfortunately, it's not, can you show up with hydrogen and stick it into the unit and expect it to run? Maybe the combustor is ready, the thing that actually turns the fuel into heat, spins the rotating equipment, turns the generator, etc. But you have balance of plant, you have equipment, you have personnel, you have operating profiles that also have to be considered. So again, a few examples on demonstrations. Here's a list of the upcoming projects. You can see more work on electrolyzers and their integration. We're looking at pyrolysis technology, so that's integrating the gas network to make hydrogen on site using gas delivered. So natural gas delivered to the customer, the technology converts it to hydrogen at the site, and then the customer uses hydrogen instead of natural gas. That natural gas, the carbon, goes to a solid product, which either gets turned into a byproduct or stored somewhere else. We're looking at other types of fuels, looking at pipelines, looking at CO2 capture and distribution across industry. So again, co-locating CO2 management, trunk lines that, where 45Q is very helpful to ethanol because ethanol produces high concentration of CO2, so they get a lot of value and a tax credit. Whereas you go to natural gas power plants, that value is diminished, the capex goes up incredibly high. But looking at it as an ecosystem and doing that systems planning becomes where there's an opportunity. And then in addition to that, what we're really excited about though is the efforts that DOE and others worldwide, not just in the US, launching around these hubs. There's hydrogen hub that gets a lot of attention. There's carbon management hubs going on. There's industrial decarbonization, but we're leading an effort in addition that looks at how to integrate that knowledge sharing again. You see in the news all the time projects being canceled. Hydrogen just didn't work out. Biofuels that didn't work out. CO2 pipelines coming into question. This is a natural part of the transformation. This is technology coming to terms with the scale at which it has to commercialize, with public acceptance and understanding. And hubs provide a very unique opportunity to get all stakeholders working together. And through this initiative with the LCRI, we're engaging with all of the hydrogen hubs, but two in particular we have very strong engagement with that are working towards they're moving forward. You can find information there. And really speaking to the reality that there is a lot going on in this space. There will be bumps along the way. We're going to try, very hard to lend our objective and independent analysis to focusing on the areas that are going to make the biggest impact right away. And then lastly, I'll leave you with a little teaser. We've got a new net zero analysis coming out. And I've mentioned all these topics already with the exception of the middle one, which is the new EPA power plant rules for the US and what that could do for power generation and net zero. But what I'll end on, and certainly it's probably recognized by now, the pace of change we're talking about is intensifying. And so we have recharacterized this initiative since we started looking at net zero to address that pace of change. We recognize we're not the only ones out there, and we really value these types of opportunities because we hope they will increase the amount of communication and coordination that we can create across the energy system. So Charlie, with that, I'll turn it over to you.
Okay. Jeffrey, that's quite a nice tour through what's going on in the world out there in the decarbonization side of things. So before we jump into the Slido questions, I have a question that kind of was following my trail through the presentation here on economics. I'm curious, has there been enough work done that you can get a feel for what the economics of some of these pathways look like? Are there some pathways that just fundamentally look attractive than others because of fundamental limitations or economic limitations?
It's a really interesting question.
Two.
So I would say what we learned in doing our first net zero analysis was the economic pathway and the human factor don't always align. So one example is our net zero analysis shows that if we allow for bioenergy with CCS to help offset emissions from hard to abate sectors, particularly aviation, then there is a potential economic pathway that gets the economy to net zero without introducing new sustainable aviation fuels. Now, of course, you see out there airlines, airports, other stakeholders working towards decarbonizing aviation. And not to pick on them, it's just one that's an example. There are other examples. And the hard part is the macroeconomics sounds nice if they can be streamlined, but our economy doesn't work that way. Our economy doesn't take a policy perspective that the economy is working as a whole. And not to turn this into a policy debate, but the economics, the technology viability, they lend themselves to not always be in sync. And you see this time and time again with economic models. They're never, it's not that they're meant to be right, but they're certainly never accurate. And that's not what they're intended to do. Now, there are some examples where the economics of some of these technologies may not work out, but it's not always clear exactly why. So, for example, before 45V with the production tax credit on hydrogen, it wasn't really clear that hydrogen could play a role until maybe some substantial cost drivers came into play. Largely CapEx and the cost of electricity were driven down far enough, which maybe could happen in the later part of the mid-century. But then tax credits come along, policy comes along to incentivize. And so then there's another set of dynamic that emerges. There's a lot of debate about 45V, and we won't go into that either. But
Yeah.
there's this kind of understanding of we're trying to decarbonize the system with technologies that aren't yet at scale to reach the economics of that future. And what are the pathways to get it there? Well, there's a lot of pathways. You can set a carbon price, you can create an energy policy, you can do production tax credits and investment tax credits. Uh, every country has a slightly different approach to all this, and they're all generally moving in the same direction. It doesn't look like any one approach is really there. So yeah, there are some cases where there are technological, thermodynamic boundaries, but largely that's not where we're running into challenges. It's putting together all of the pieces of the policy, the regulatory, the public perception, the technology costs and availability that's becoming the challenge. And our approach is that's a lot for anybody, one organization or any individual company to comprehend. So our approach is put the technology in the field, the a smart technology that's going to largely pencil out, objectively speaking, uh, and let let the stakeholders come and learn from it and share those learnings as far and as wide as we can, because we just never know where the next innovation is going to come from.
Complex question, and then when you throw in the human factors, it's even more complex.
Sure.
Okay, thanks for that. Now let's look at a couple of the questions here. Speaking of carbon capture has had a checkered history. What is your view of the outlook?
Well, it certainly, yeah, I would agree. It has a checkered history. 80% of primary energy today comes from fossil fuels. 80%. Even today, most of the decarbonization that's happened in the electric sector has come from transitioning from coal to gas. We believe, in our analysis, and this is based on analysis, that CO2 transport, storage, capture, the whole value chain will be integral into this net zero transition. We recognize, though, that it doesn't fit everywhere. It doesn't necessarily fit all regions. It doesn't fit, every country, doesn't fit every community. But at a macro level, without CCS, we don't see an affordable, reliable pathway to that net zero. There's other things that make this obviously more complicated because there are no real technical limitations to CCS. There certainly are economic boundaries. There are public perception. There are environmental and regulatory. But our analysis shows that without CCS, it's going to be very expensive and very challenging to maintain that affordability and reliability piece of the energy system moving forward.
Interesting. Thank you. Question here from Russ. Moving energy across time is a primary challenge of critical importance, but hydrogen transportation and storage do not appear practical. Have you looked at ammonia?
Yeah, we are looking at ammonia. As I mentioned before, unless you're sitting on top of salt caverns, hydrogen is going to be really difficult from an infrastructure perspective. Of course, the challenge with ammonia is you're going to lose energy in the conversion to ammonia, and can't use ammonia. You got to convert it back to hydrogen as something else. There's another energy loss. So you're now having to use time and resources to aggregate, and you're going to burn through that, to use the pun, more quickly than you're going to create it. So the global market for low carbon fuels certainly has a keen eye on ammonia. You generating ammonia from natural gas with carbon capture in the near term, maybe using excess low cost electricity to make hydrogen and then synthesizing the ammonia from there. But of course, everything has a thermodynamic penalty, everything has a cost. So in that case, when we look at ammonia, we're considering it for specific use case, all these low carbon fuels, specific use cases, specific regions, and how the energy systems play together to make that affordable potentially.
Okay, thank you. I think we'll try to squeeze in one more question here. MISO's RIA study showed no need to add dispatchable generators, gas or other, if we can build transmission quickly enough. What are your thoughts on this?
So that gets outside of my area of expertise, but I think we'd have to follow up. I believe we have some EPRI work on the benefits and opportunities with moving electrons across transmission systems, especially in a net zero world. Our net zero analysis does assume that there would be transition build out across the different regions. So there is a transmission, and what that would take, I think it's 2 to 4x, 2x what it is today, more than 4x what it would be if we limited the options. So even, we'll go back and check, but I believe even with the ability to have the transition from one resource rich area, renewables rich area to another, there's still parts of our economy that will rely on a low carbon molecule and a fuel. And, you know, if you're trading with one area, odds are that other area you're trading with is trading with someone else. So in practice, it sounds like a good idea. It's still a challenge. So it's something we can definitely follow up on though to get a better
Okay.
answer.
Well, thanks for that, Jeffrey. Okay, so we're just a little past the top of the hour, so we're going to need to wrap it up. I want to thank Jeffrey for this very timely and informative presentation, and I hope you all have a better appreciation for the role of molecules in our future. As I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to and get them posted as quickly as possible. We appreciate your engagement and look forward to seeing you again soon. Have a look at the announcements on our upcoming webinars in September and our fall technical work in Providence, Rhode Island in October. Further information on all of our webinars and meetings can be found on our website at esig.energy under events and in our newsletters and informational emails, and you're all invited to attend. Jeffrey, thank you once again for this really informative webinar. Thanks to all of you for your engagement. We look forward to seeing you again in the near future. In the meantime, everyone, take care, stay safe, and thanks for your participation. See you soon.